4 out, and we're going to be able to use the substitution right here for that. Oh, okay, I know exactly what we're doing now. Okay, so from here, we're going to set x, where x equals sine of theta, but now we're going to need to set something in front of it so that we can get 1 minus sine squared theta underneath here. The only way that we can do this is if we get rid of this 4, which means we're going to need to have 2 sine of theta. This is because when we input 2 sine of theta in for x, we're going to end up getting it at 4 sine squared theta. So we'll go like this. So dx over, let's substitute our x in over here, so 2 sine theta times the square root of 4 minus 2 sine theta squared. All right, from here we're going to have dx over 2 sine theta times the square root of 4 minus 2 squared is 4 sine squared theta. We are now able to take out a 4 in that area. So it will look like 4 times 1 minus sine squared theta. And because they are now multiplied together, we can take this 4 out and we can take the square root of it. So dx over 4 sine theta, I'm just multiplying this 4 out when I multiply it, times the square root 1 minus sine squared theta. Now sine squared theta equals cosine theta, or no, cosine squared theta. So we're going to have over dx 4 sine theta times cosine squared theta. And now, as this is only going to be positive from all values, no, for values such that cosine is positive, actually no, for, yeah, no, not the cosine being, yeah, for cosine being positive, we're going to just assume that, because otherwise we'd have to have plus minus. So this will be dx over 4 sine theta times cosine theta. From here, we can take 1 over 4 out. So it's the integral of dx over sine theta times cosine theta. Let's see, how can we go from here? I think I forgot I forgot to change over dx. That will explain it. So x equals 2 sine theta. Now we're going to want dx is going to be equal to 2 cosine theta, which means that we're going to have to put 2 cosine theta on top of everything, d theta. Yeah, otherwise it would be really be a big pain for us to integrate the this right here, the sine theta times cosine theta. All right, so from here we can cancel our cosine thetas. And then we get 1/2 times the integral of d theta over sine theta. And then 1 over sine theta is also equal to the derivative of, well, let's see, 1 over sine equals CSC theta. So it's going to be the integral of CSC theta, d theta, to all that times 1/2. And actually, I think, think I'm forgetting something here. This was x squared, so there's another tiny mistake I made right there. All of this is supposed to be squared.
Um, oh wait. If it's x squared and x is 2 sine theta, then the overall you have to do 2 sine theta squared.
Yeah, so that means that's going to be a 4 also. I'm going to say good catch there also because, yeah. So this is technically 2 sine theta squared, which means that this is going to be 4 sine theta, which means the whole way down I need to fix this. Very good catch there on my algebra. All right. So now we are at the integral of CSE squared theta, d theta, all of that times 1 over 4. And this integrates, the integral of this is going to be cotangent, I believe. Wait 1 minute. Opposite cotangent. So we're going to have 1 over 4 on the outside, and this is going to be the integral of cotangent, or opposite cotangent, theta, plus c. And now we're going to have to create our right triangle. If we remember correctly, we said x equals 2 sine theta. So this is what we began with. Now let's divide everything by 2. So x over 2 equals sine theta. So sine is opposite over hypotenuse. So this x right here is going to be our opposite, and this 2 is going to be our hypotenuse. Wait, oh, and I just wrote 2 twice. So x is going to be opposite, 2 is going to be there. So now we're going to use a squared plus b squared equals c squared. We're going to have 2 squared plus b squared equals x squared. So b squared equals x squared minus 4, and b is going to be equal to the square root of x squared minus 4. So this last side right here is going to be equal to the square root of x squared minus 4.
Hold on 1 second, Jason. Look back at the original integral. And
Yeah.
so, okay. So when you observe that integral, you see, what would be if we did the sine thing? Let's see. And so let's see. Well, the thing is, you can use that actually to determine the third side of the triangle when you do it. And so actually, I think this is a good bit of advice. Like when you're trying to make the triangle, you can actually make that. Sometimes you can make that the third side, which is what I usually do. And usually that's the correct way because when you're doing the trig sub.
Well, it looks like it's slightly different. It looks like this is x squared minus 4 instead of 4 minus x squared. But yeah. Just because otherwise, like, because this, yeah, well, this is already equal to sine, so it kind of makes sense for that. You can just switch the two because your cosine and sine are very similar. But yeah. Let's see, actually, no, I did this wrong. Yeah, actually, you're right. You are 100% correct because I misput in a and b because this is supposed to be x squared plus b squared equals 2 squared, which means that b is going to equal to the square root of 4 minus x squared, which is exactly what yep, that was exactly what you were saying. So, Ethan, thank you. That was right on it. So this right here. Oh. and this right here equal. And I think that's probably a very good shortcut-ish type thing on some parts of it. So we're going to have to find, so we're going to have opposite 1 over 4 cotangent theta plus c, and then we're going to have to solve for theta. So, cotangent, the inverse of theta, that is going to be equal to the adjacent over opposite. So that will be x squared minus 4, all that over x. So we're going to get opposite 1 over 4, cotangent opposite 1 of x squared minus 4 over x plus c. That is, yep, I think that's correct. Because that would mean, yeah. Or no, because this is supposed to be that's supposed to be cotangent.
Actually, you don't need to have arc cotangent because you're not solving for theta.
Well, actually true. Because we
You
are
would
solving
just
for, here, wait, let's see. So we're solving for, oh wait, no, we just need to solve for theta, right? And then it's going to be cotangent of whatever theta is equal to, so it doesn't need to be arc, right? So it should just be x squared minus 4 over x, like that.
well, I think well look at what the work you did on the right and look at the variable you're trying to solve for. What do they have in common?
Oh, crap. Yeah, this whole thing is equal to this.
Exactly.
Yep, that makes a lot more sense.
Yeah, so you're not solving for theta, you just solve the whole thing.
Yeah,
So all
that'll
you have
be,
to do is plug that baby in and boom, you are done.
and you know, that saves so much more time. I think I should just do that for all of them. I think, because isn't one of the methods you just solve for the inverse, or? Oh, never mind. Okay, never mind. I'm getting ahead of myself.
Yeah, don't try to overcomplicate things
Yeah.
too much.
So it'll be opposite x squared minus 4 over 4x plus c. Okay, that was a
And that should
nice. Hmm?
and is that the right answer
Oh,
in the textbook?
actually, I've been writing it incorrectly the entire time.
Oh, 4 minus, yes, 4
Yeah,
minus
it's
x squared.
supposed
I
to be
didn't
4
make
minus
note.
x squared, not. We even proved it right there, and I
Oh,
still did it
yeah.
wrong. And then, yeah, that's I think it's the correct answer. I'll take a look in a second.
All right.
And compared to the one in the textbook, that is correct. Okay.
Excellent. Very
Ooh,
good.
getting somewhere slowly. I went one whole problem without any issues, and then I got into this one.
Ah, that's fine.
Okay, time for 41.
Let's do it.
Yep. Okay, so
Yes.
wait, and this one because I'm using the answers to like the base because I don't have the other thing open. So oh, there we go. I'm just trying to figure out what the thing is so I don't have like 20 tabs open. So it's going to be the square root of x squared minus 4 over x dx, and then we need to solve it. So let me just hide that real quick. So we got an x squared minus 4 times the square root. If I'm correct, that is cotangent. No, not cotangent. Cosine. Uh, yes, I think. No,
Well,
it's not.
it's,
It's
think of
oh
your trig identities.
yeah,
Which
it's
one does
secant.
it look like?
Looks like
Yeah,
secant.
there we go.
Or not equal to, but they parallel. They're. I guess I'll just put parallel or something. I don't know. So for this one, we're going to want to set x equal to, well, this is tan squared theta plus 1 equals secant squared theta. And honestly, I should just write all of these identities down. I think that would make it easier in the first place whenever I do these. So that means we're going to say x equal to secant theta. And then because we need to get that 4 out, we're going to have it equal to 2 secant theta. And before I forget, like I did last time, so dx is going to be equal to 2 secant theta tangent theta. So we're going to go and substitute in our new values for x. So it is going to be the square root of 2 secant theta, all this squared, minus 4 over a single x, so that'll be 2 secant theta. And our dx is going to be equal to 2 secant theta d theta. Oh, no, tangent theta. All right, so from here we can cancel out, we can actually cancel out our secant, 2 secant thetas. So now we're going to have the square root of 4 secant squared theta minus 4 times tangent theta d theta. And no, I need to write d theta right there. So we can take the 4 out, and because the square root of 4 is 2, it'll be 2 times the square root of secant squared theta minus 1 times tangent theta d theta. From here, we will use our trig identity, in which tan squared theta plus 1 equals secant squared theta, and then tangent squared theta equals secant squared theta minus 1. So we're going to get 2 times the root of tangent squared theta times tangent of theta d theta. We can take that 2 out to the front, and when we take the square root of tangent theta, where it is positive to 1, so between opposite x over 2 and opposite pi over 2 to pi over 2, we're going to get 2 tangent theta times tangent theta d theta. So now we're going to want to set u equal to, actually we might have an issue here.
I believe you are almost on the.
Because never mind. I see what this does. I don't need to do u yet because that's tangent squared theta, which we can just reuse this thing to set it back.
Mm-hmm.
That makes so much sense. So we got 2 times tangent squared theta d theta, and then we can use our secant square. We can use secant squared theta equals tangent theta. Wait, we can just use this one right here. No need to rewrite it. So we get 2 times the integral of secant squared theta minus 1 d theta. All right. So from here, when we take the integral, secant squared theta is equal to tangent. So we got, I don't need that integral sign again anymore. So we're going to have 2 times tangent theta minus theta plus e. Now we need to solve for theta and tangent theta. So we're going to I'll make our right triangle right here, where tangent is opposite over adjacent. And let's just go back to what we had originally. Wait, we had x equals secant theta, or 2 secant theta. So that means x over 2 equals secant theta and secant theta is the 1 over cosine. And cosine equals opposite over, no, not, adjacent, no, 1 minute, A over H, which will mean that secant is going to be equal to H over A. So our hypotenuse for this equation is going to be H, no, it's going to be X, and our adjacent is going to be equal to 2. And when you can use the x squared minus 4 this times the square root to find the last bit like we saw earlier. Okay, so that means tangent of theta is going to be equal. Tangent is opposite over hypotenuse. So it's going to be equal to the square root of x squared minus 4 over 2. So we're going to have 2 times x squared minus 4 over 2 minus, and now we must solve for theta. So I guess we can just take it right off of tangent theta for this one. So theta equals the opposite tangent, no, arctangent of x squared minus 4 over 2. All of that plus c. And let me take a look. I just want to compare it to see if we got it correct. It looks like the book got to a different answer, but they also used secant instead of tangent inverse. No, so they used secant inverse instead of tangent inverse. I don't feel it's going to make a big difference as they'll both get you the same angle. So,
Actually,
is it an issue?
yeah, I believe so. Go back to x equals 2 secant 0. Or, yes. Well, x over 2 equals secant 0.
Oh yeah,
And
right here.
that's how you solve. So you would have to solve for theta in that equation.
Okay, that kind of makes sense. But I don't know why it exactly would have to be exclusive to that.
And I think that should reflect the. Does the book say?
That is exactly what the book has
Yeah,
as the answer.
because yeah, the other one wouldn't. Yeah, it wouldn't be equivalent.
Hmm. So theta equals sec opposite
Or maybe
1
it
of
would
x over.
be,
It
but
should
I think
in theory be equivalent, but it's also a much uglier looking answer.
yeah, it's much more convenient.
Yeah.
Yeah,
But it should be the same because theta is just theta all the time. Because it's just the theta of this angle, and the angle can be measured from any number of things. So it should be fine without, but yeah, why
yeah. I
not?
suppose Professor Connolly wouldn't mark it correctly.
Well,
So yes, yes,
yeah, he might mark it
you,
correctly, he might not. We don't know.
yeah, I suppose so.
Okay,
Hey.
so that was very, it went a lot smoother. So now we're going to move on to number 43. And number 43 is the integral from the square root of 2 to 2 of 1 over t to the third power times the square root of t squared minus 1. And that's all dx. Okay, so that's supposed to be secant. So I'm just going to go through and find until I find the one which resembles what is right. So tangent squared of x or theta equals secant squared theta minus 1, which that looks right about right for this problem right here. especially since we don't have to substitute anything else in for it. So we are going to let t equal secant theta. That way we can get our tangent theta in a second. So I'm going to just solve the indefinite integral first. 1 over, we're going to input this for t, so it's going to be secant 3 to the third power theta times the square root of secant squared theta minus 1, and then we need to find dx real quick, or a dt actually. This is supposed to be dt. So dt is going to be equal to secant theta tangent theta d theta. All right. So from here we are going to substitute. We're going to use the tangent squared equals secant squared theta minus 1, and we're going to simplify this part underneath. So it's going to be 1 over, well, actually, no, we're going to get rid of that one. We're going to put secant theta tangent theta d theta over secant to the third power theta to tangent squared, no, times the square root of tangent squared theta. From here, we can cancel out 1 secant. So we're going to rewrite this as tangent theta d theta all over secant to the second power theta. And then we have the square root of tangent squared theta, which will just be tangent theta. This gives us a chance to cancel out our tangents. So we're going to have d theta over secant squared theta. Now I'm pretty sure we're going to have to go and split this apart. Because I'm trying. Oh wait, no, actually no, we don't, because this is equal to cosine squared. No, yeah, cosine squared theta d theta, which makes it a little bit easier to work with. And then from here, we're going to use the we're going to break this power down using cosine squared theta equals 1/2 1 plus cosine of 2 theta. So we're now going to have the integral of 1/2 times 1 plus cosine of 2 theta d theta, where we can take the 1/2 to the front. From here, we can integrate. So we're going to have 1/2 times, we're going to have theta plus, so if we take the integral of cosine, we're going to get sine of 2 theta. And because we have to use u substitution, this is going to be 1 over 2 in front. We're just going to skip over that step. And then that's all going to be plus c. So now that we have all this, let's see, is it going to be easier to input our values for theta and then get an answer, reverse it out? Let's see. So t equal, no, it's just going to be, so we're just going to go and restate the bounds with by substituting back in for theta. So we're going to draw our right-hand triangle. And we had t equals secant of theta. And secant of theta is equal to h over a. So we're going to have, so t is going to be our hypotenuse, and our adjacent is going to be equal to 1. Which, if we take a look down over here, this is what's going to, well, exactly what we're going to have for our third angle, for our hypotenuse. Oh no, for our opposite. Which we can get through a squared plus b squared equals c squared. All right, so from here we need to find sine of 2 theta and theta. So we're going to have to, kind of a little stumped on the 2 theta part. I guess it actually might be easier in this case to not, and instead to figure out, readjust our bounds. So, because I can not tell you that off the top of my head. So we have 2 and root 2, and we set t equal to secant theta. And I think that's all we're going to need. So that means the secant of opposite 1 of t is going to equal theta for us, which will become our new bounds right here and here. So the secant inverse of 2 is going to equal, this is 1 over cosine. So we're finding 1 over cosine inverse, which will mean that this is equal to whatever makes cosine 1 over 2. So this is going to be pi over 3. That's because if you take that, it will equal, because cosine at pi over 3 equals 1/2, and that means 1 over cosine at pi over 3 is going to equal 2, because you just switch them. So if we have, the other one is going to be at square root 2, which I know that is at pi over 4, because that's the only place on the unit circle that you can get pi over 4 at. So the cosine of pi over 4 equals root 2 over 2, which if we take the do it like, write it like this, right as that one. So 1 over cosine of pi over 4 is going to equal 2 over root 2, and if we multiply by root 2 over root 2, we're going to get root 2. So our new bounds are going to be from pi over 4 to pi over 3. Let me just check. Yeah, so pi over 4 to pi over 3. And actually, this is going to be for evaluated, not here. That's the indefinite. So 1 over 1/2 theta plus 1 over 2 sine of 2 theta from pi over 4 to pi over 3. Yep. All right, so now we're going to solve. So it's going to be 1 over half, or 1/2, times pi over 3 plus 1/2 sine 2 times pi over 3. All of this is going to be subtracted by pi over 4 plus 1/2 sine of 2 times pi over 4. Now we simplify it down, so it'll be 1/2 times pi over 3 plus, 1/2. Sine at this value is going to be 1/2, because sine at 2 pi over 3, when you draw it out in the unit circle, it'll, actually no, that's going to be root 3 over 2, not at 1/2. Minus, now we're going to distribute this, so it's going to be pi over 4 minus 1/2. Now sine at pi over 2, that's going to be equal to 1. All right, so 1/2 times pi over 3 plus root 3 over 4 minus pi over 4 minus 1 over 2. And let me take a look. So I believe we can simplify this a bit more if we wanted. So first we can distribute, so it'll be pi over 6 plus root 3 over 8 minus pi over 8 minus 1/4. And then we can combine the pi terms. So we can 6, 12, 18. We'll just multiply by each of the other values of them. So we're going to have 8 pi over 8 times 6. That equals 48. So that'll be over here. Minus 6 pi over 48. Plus root 3 over 8 minus 1 over 4. So that is going to be equal to 2 pi over 24 plus, or no, over 48, not 24. Plus root 3 over 8 minus 1 over 4, which we can simplify down to pi over 24 plus root 3 over 8 minus 1 over 4. All right, and we were able to do number 43. Okay, so from here, I think we can go on to number, let's see. Oh, in 45, why does the up or down turn into pi over 4? Okay, so we're going to want to look right here at this. So, well, we have the unit circle. Let me just draw it out again, just because I find this is the best way to help me visualize it and think about it. So we have the root 2 over 2, root 2 over 2. This will be root 3 over 2, 1 over 2, 1 over 2, root 3 over 2, and with these inner values being for cosine, and these outer values being for sine theta. So we know that whatever value we have for secant of theta is going to be equal to 1 over cosine of theta. So let's say we have our secant of theta is going to be equal to 2, because I believe that's what the 1/4 was, if I was correct. Yes. So that's going to mean 1 over cosine theta equals 2. Now let's multiply the cosine across, so 1 equals 2 cosine theta. And then let's divide that 2 over, so 1 over 2 equals cosine theta. So, or wait, did I, oh, this is for secant equals 2, not root 2. We'll do root 2 in a second. So that is for, to prove this one right here, for 1/3. And then let's say we have instead the other scenario in which secant theta equals root 2. Well, that will be equal to 1 over cosine theta equals root 2. Multiply the cosine of theta over. So that was 1 equals root 2 cosine theta. And that'll be 1 over root 2 equals cosine theta. For this, we then now need to multiply by theta, no, by root 2 on the top and bottom, which will give us root 2 over 2 equals cosine theta, and therefore theta equals pi over 4. Does that answer it, Adam? Wait, no, Adam's not even in this. Oh my. I just realized I just explained it for Adam, and Adam's not even in this.
That's
Where did you
unfortunate.
see it?
I'm not sure what. I'm not sure if that, because I think we got like the answer is right, but for some reason I'm getting a. I don't know. Does that say for that question the answer in the textbook is like
Yeah, the answer in the textbook is it's lining up. Well, here, I'll double check it in just a second.
All right then. Just want to make sure we're on the right page here because I
see.
do think I got it, but
Oh, this is for, let's see, for 43. Let me just check the steps. Okay, so they got to that point also. I think they used a slightly different no, they somehow got to there. Just here, I'll copy and paste the textbook solution. And I will put it right here for everyone. If it will, there we go.
That would be bit. Oh
Because you,
yeah, I see it now. Yeah.
yeah. I mean, my work's
Hmm.
just, I don't think as neat as the textbooks, but it still gets the similar idea. It just took me forever because I only solved for the bounds in the very end, and then I just explained why
Okay,
it's,
yeah, that's good then.
yeah.
I don't know if he cares if we like
It
simplify
doesn't,
it down that much.
I don't know if, he might be fine if we just leave it like this, one of these two. Um,
Yeah,
or
because as long as it's
yeah, because, I mean, I think he prefers this. Or he might not care if we leave it as four terms, like it was left, right, here. I think this might be fine. Oh,
well, that's good then.
yeah. Oh, and of course, whenever I highlight it, it just wants to go all over the page.
That's Windows for you.
Yep.
Likes to go crazy.
Yeah, this version, I normally use the other version of OneNote. This is just, I find this one to be more easier with all the pens.
Yeah, so that's good. All right,
Um,
solid.
I guess let's go on to 45. And also, if anyone has any specific questions or they want to give it a shot, feel free. It's just, I'm just going to keep doing them until I either get them wrong and I need to get corrected, or I get them right. So this is going to be the integral from 0 to a of dx over a squared plus x squared to the 3 over 2. All right, so in this we have a squared plus x squared as to that. So let me just figure out which term we are going to use on this. So tangent squared theta plus 1 equals secant squared theta. This does not work. Um, Sine squared theta minus 1 equals cosine squared theta. That also does not work. And neither does the other one because that term is positive. I think that leaves us with tangent. No, wait, no. Tangent didn't work. Oh, wait, no, wait, no. Because this can all, wait, no, tangent will work. Because 1 plus tangent squared theta also equals secant squared theta. Okay, so yeah, we're gonna use we're gonna set x equal to theta. So here I'm just gonna rewrite this into a little bit easier for me to see. Pretty much break that out. And then we're gonna set x equal to a squared tangent. No, just a tangent. A tangent theta. So that was going to give us from the bounds from, well, since we're substituting, I'm just going to use alpha and beta right now. And then we need to solve for dx in just a second. But that will give us a squared plus a squared tangent squared theta from us substituting into the x squared. And our dx is going to be equal to a. That is going to be secant squared theta. So a times secant squared theta d theta. All right, so we can now, from a to beta, or from alpha to beta, we're going to have a secant squared theta d theta. We're going to take an a. We're going to take an a outside. And we can do that because there's an a squared there and an a squared right there. So we'll just take an a out in parentheses and then further. All of this is cubed. So this will mean from alpha to beta, we're going to have a secant squared theta d theta over a times the square root of, I think that's secant squared theta. Yep, secant squared theta. Let me just check the identity real quick. Yep, right there. All to the third power. So now we're going to get from alpha to beta. The integral of alpha to beta is going to be equal, what is going to be a secant squared theta d theta all over a times secant theta to the third power. So now we're going to distribute that. So it is going to be from alpha to beta of a secant squared theta d theta over a to the third power times secant third power theta. So from here we can notice that we can cancel out an a, and we can cancel out some of our secant to the third power, or we can prevent it. We can get rid of it to the third power. So now we get from alpha to beta, we get d theta over alpha squared times secant of theta. From here we can take, as alpha is a constant, we can go and take 1 over alpha out, and then it's going to be from alpha to beta, or no, we're going to take 1 over a squared out, and it's going to be from alpha to beta of d theta over secant theta. Now secant theta equals 1 over cosine theta, so we're now going to have 1 over a squared from alpha to beta, or times alpha to beta, the integral of alpha to beta of cosine theta d theta. So now we're just going to draw out our little triangle here. And we're going to want to see what we had to begin with. So we had x equals theta tangent x. So that means x over, wait 1 minute, is that what we had? I wrote that wrong. Whoops. That means x over a equals tangent of theta. And tangent is equal to opposite over adjacent. So that means our opposite is going to be x, and our adjacent is going to be a, which we can also see right here as this should be our third side, which we can get through a squared plus b squared equals c squared. So this is going to be the square root of a squared plus x squared. Now we need to get cosine of theta. So cosine of theta, that's going to be equal to adjacent, so a over hypotenuse, which is the square root of a squared plus x squared. All right. So actually, no, let's actually integrate this first, and then we'll find that. I just realized that would probably be a good call. So this is going to be the integral of cosine theta is going to be sine theta. And this is going to be from alpha to beta still. So we're going to get 1 over a squared. Now we have to solve for sine of theta instead. So sine is going to be opposite over hypotenuse, so that'll be x over root a squared plus x squared. So we're going to have 1 over a squared times x over a squared plus x squared, which is the square root, from 0 to alpha, 0 to a. All right, so 1 over a squared times, so we're going to begin by plugging in a, so a over the square root of a squared plus a squared, and this is going to be minus, we're going to plug in 0, so 0. Now we can simplify this, so 1 over a squared times a over the square root of a squared plus a squared. We can simplify this out to 1 over a times the square root of a squared of 2a squared, which we can simplify one more time to 1 over a squared times the square root of 2. Let me just check the answer. And yep, that is the correct answer for this problem.
Alternatively, I believe in the beginning you could have actually used the like solved for theta for the bounds.
I probably could have solved for the bounds. That's actually what the book did, but I just solved the indefinite first, so.
And then that gives you 0 and pi over 4, which eventually I believe does give you the same answer.
Yeah, here, I can actually copy the solution they gave. And I'll put it right here for anyone who wants to see the other way to do it.
I don't know why they converted back into the raw form instead of keeping it square root of 2 over 2a squared in that one. That's weird.
Like, what do you mean by that? Like,
Because, like, 1 over the square root of 2, you shouldn't really have, usually math notation is you shouldn't have a radical in the denominator.
that is
Because that,
true.
yeah.
So it really should be if we take it one step further.
If you
Root
multiply,
2
yeah, by
over a
2,
squared, or over 2a squared.
yeah. It's just like math cleanliness, kind of like ln, I suppose. But
Yeah.
well,
I mean,
like
as long as
transfer.
he's not grading us on it, we should be, for the most part, fine.
Yeah, it's equivalency.
Yeah.
And
Okay, so.
amount points are the modus operandi of the issue or the problem.
Hmm. So I think I want to handle one of the challenge problems and then call it after that, because I will say, Ethan, thank you so much because you've been helping a lot and you sorted out most of my stuff.
I mean, anytime it's great to study with a friend.
Mm-hmm.
I mean, a classmate. I mean, I guess we can be friends.
Yeah.
Mhm.
We're all friends
But
here.
yeah,
Okay, let's see.
we share or something. But that's okay.
I just want to check. Are we working on 6.2 right now?
Yeah, I believe
Yeah.
so.
Okay, so if I could only read what, because these solutions are terribly copied over, so it's very hard to tell what the initial thing is. I guess we'll do 65. All right, so 65, it looks like, oh, hello. 65, it looks like it is S equals f of t, which equals from 0, I think that's to L. He made this very tiny to read, and I should probably just pull it from the book, but
Yeah, just copy the problem.
So like, if people want to do it.
Well, that's what I'm trying to, but it's
All
just
right.
so tiny, like it's very small writing that I cannot read it. Let me just pull it up in the actual math book if I can find that.
Uh, well, we're getting a few more people here.
Yeah,
Up, new faces. Welcome, welcome.
we're having a bit more of a party.
Yeah, nothing like math parties. That's what they used to do back in like the 1600s, when like the only people who really knew math were Isaac Newton, that Gottlieb guy, and just a few other nerds. I mean, Da Vinci. Love that guy.
I mean, hey, now they are all getting us employed later after we complete all of our calculus. Okay,
Yeah.
I just pulled up section 6. Let me get to 6.2, and then I will get to the questions and wait,
No,
wait, is this 6.2 or is this 7 point something? No, is it?
it's not 7 point. This is 6.2. This is trig interval.
Okay.
7.2 has to do with like areas.
Mm,
This too, but like areas on graphs usually.
yeah. Oh, is this? Partial fractions. Oh no, there we go. Trigonometric integral. Yeah, I was just clicking on the wrong thing. That would explain it. I was like reading the partial fractions. I'm like, we just did that. Okay, so this is 65, which reads a particle in moves on a straight line. Oh, so it stops scrolling down. Particle moves in a straight line with velocity of the function of v of t equals sine wt cosine squared wt. Find its position at s equals f of x if f of 0 is 0. And let me just copy this over real quick so that we have it right in front of us, as it's a lot easier to read. Okay, there we go. So we know that the position is going to be equal to the integral of velocity. So we're going to know that the integral of sine of wt cosine squared wt from 0 to s, or I believe it should be from 0 to s. A straight line, find its position s equals f of t if f of 0 equals 0. I guess, oh no, it's just asking for, I guess, a general constant here, which we'll just call, I don't know, we'll call it L. Actually, no, we'll call it S, because that just makes sense. Okay. So from here, we can probably use U equal, actually, let me just see how this is written. Equals WT. Oh, and this will need to be DT. Okay, yeah, because T is going to be, so W is just a constant right there. All right. So we're going to have from 0 to S, or truly any constant, I guess. We'll just use a capital B. I don't want something that's too confusing so that I can't, when I go back later, I don't understand it. So that is going to be, I'm going to have to take a look at this. I'm going to say we're going to just try cosine squared cosine squared of x equals 1/2 1 plus cosine of x, no, of 2x. And then in this case, we have x is going to be equal to wt. So instead, we're going to have the cosine squared of wt is going to be equal to 1/2 times 1 plus, oh, let me get the 1. 1 plus the cosine of 2 times wt. All right, so now we have sine of wt. Or actually, I think it's just sine of, no, yeah, sine of wt times 1/2 times 1 plus the cosine of 2wt dt. We can take this 1/2 out to the front. So it's going to be the integral of from 0 to beta, where beta is just any time after 0, of sine wt times 1 plus the cosine of 2wt dt. And we might as well use substitute in real quick. So we're going to set u equal to wt, which just means du is going to be equal to w dt, which means 1 over w is going to be equal to dt. So we're going to take 1 over w out to the front, so 1 over 2w from 0, and we're going to now use c to represent as we're changing our bounds with u substitution. So we'll use c as our placeholder of
Jason,
sine.
may I stop you for a sec? I
Yeah.
think you're overcomplicating the problem a little bit. You actually, if you go back, the thing is,
Oh.
to the very beginning, it's actually use substitution.
Oh,
mean,
and
yeah, take a
you're
because I
so
think
right.
he did this in class, and well, I kind of shouldn't.
I mean, it looks very familiar, I'll be honest. But yeah, I did
And yeah,
overcomplicate it.
so
Because like I'm just realizing like this whole thing is like it's a little excessive. Oh,
yeah, it's really it's a much simpler problem than it looks if you know what you're doing.
okay, then
Because
let's
the WT, the omega
yeah,
T really.
because
Uh,
let's say we put u equal to wt, du equals no, wdt.
but what's the single like? What's the factor to the first degree in
Wait,
that you
sorry.
can eliminate?
Wait, say again?
Like, so there's a factor in the first degree that you can take out by doing a proper U substitution.
The wt, like the w?
Not just that. No, there's more to it.
The sine?
Yeah, the entirety of that. And how do you get rid of that?
This can be getting rid of if I'll be honest, I am a little stuck on that. Unless you set u equal to sine of wt,
No,
that wouldn't work.
that. Well, try thinking cosine squared WT as cosine of WT squared.
Okay, so let me rewrite it.
Now, does it look like something you can?
Like setting u equal to cosine of wt and then taking the derivative of that to get opposite sine wt and
Try
times
that.
dt.
Yeah.
Okay, I see where you're going with this. That's actually a
And
really...
also remember your chain rule,
Hmm.
because if you don't, you're gonna miss a big chunk of the problem. So when you're doing the derivative,
It's going to be
because
W
omega,
opposite W sine of WT.
and
Okay.
then don't, and then you're forgetting.
then the DT.
Yeah, there we
Yep.
go.
All right. So we're going to have from 0 to beta. We're going to have an opposite, let's see. Because this was going to be opposite du equals W sine of WT dt. So that means we're going to have, we'll substitute this in. So u squared times opposite du. So we're going to pull our opposite sign out to the front. It's going to be 0 to beta of u squared. Well, it's not actually going to be beta. It's going to be a temporary placeholder.
Are you forgetting another constant in
I'm
your?
Oh yeah, I need to take out a W also.
Yeah.
Yeah. Thanks, Mom. So that's going to be 1 over W.
Welcome. So.
Okay, so now when we integrate it, it's going to be 1 over W times U3 divided by 3 from 0 to C. And then we can substitute in our U. So it'll be opposite 1 over W from, 2 times cosine of WT to the third power over 3 from 0 to C. And I don't know, I guess do we have to simplify this a bit more? I think so. So it'll be opposite 1 over W times cosine 3 W times C over 3 minus, the cosine is going to always be 0, which is just going to be equal to 1 over 3.
And then you can combine the two.
Combine like
you
terms.
can actually combine all of that.
Yeah, so that'll be equal to opposite cosine 3 of WC minus 1, all of that over 3W.
And, well, if there's a negative out there,
then we can bring it in. So that'll be 1 minus cosine 3WC over 3W.
And I believe that is the answer.
I don't think we can get it any more simplified than this.
No way. Let's see.
I'm pulling up the...
Well, actually, you might have to change it to... Maybe the bounds should have been actually T. 0 to T, yeah. Not C.
0 to T? Oh. Oh, that probably would have made sense.
Yeah.
I mean, technically, I can probably just get away with changing C over to T. It's not like...
Yeah, but you'd have to be real quick.
Yeah, it's like... Because that makes a lot more sense in terms of this equation. Or of this interval. And... Oh.
So yeah, so
this is supposed to be C, and then this is supposed to be T.
not bad.
So besides me overcomplicating it in the beginning, it turned out pretty good.
Yeah.
So I think let's do the last challenge one here, just because this also could be on the quiz, and then we can, I guess, if anyone has any general questions, we can just, I'll give it a shot.
All right.
Okay, so now we have question 70. Let me just pull up MindTap again. Okay, so let me copy the question over. They give us a nice little diagram.
MindTap. It sounds like a nerd heavy metal band.
Probably.
Hey man, we're MindTap. Blow your mind. All right.
Okay, so we got a charged rod of length L produces an electric field at points A, comma B, given by the following equation, which is E of P equals the integral of from opposite A to L minus A times, yeah, that. So I'll just look at this. I know this is going to be a constant because that's the wavelength. So it's pi, I think E initial, do they give an E initial? Okay, we'll see. Well, yeah, it's charge density per unit length. The rod and E's initial is the free space of permittivity, seeing the figure. Evaluate the integral to determine an expression for the electric field EP. All right, so EP equals the integral of opposite A to L minus A of wavelength B over 4 pi E to the initial times x squared plus b squared to the 3 over 2 dx. And then we will rewrite that once again. Okay, so from here we're going to have to figure out what we want to use. Tangent squared theta plus 1 equals secant squared theta. We're going to want to use this one as we have a constant right there and our x right there. So we're going to set x equal, we want to get that b squared out of there, so we're going to set it equal to b tangent theta, which means our dx is going to be equal to b secant squared theta d theta. So when we rewrite this, we're going to have it from opposite a to h minus a of value times b over 4 pi e initial times the square root of b squared tangent squared theta plus b squared, all of this to the third power, times b secant squared theta d theta. Okay, and we're fine with our current. Actually, no, we are bound. I think we're just going to set placeholders for right now. We're going to find the indefinite and then substitute it later. So it'll be from alpha to beta. So this is going to equal from alpha to beta. Honestly, I don't remember the Greek term for that. Times b squared secant squared theta d
Lambda.
theta. That's what? Sorry, what?
It's lambda. That's
Lambda?
yeah.
All right, perfect, because that's better than just trying to describe it every time. So lambda. Something like that. Dude, my spelling's probably terrible, but over 4 pi e to initial times, now because we have the two b squareds, we can take them out and put it as just b on the outside. So that'll be tan squared theta plus 1 squared. No, actually to the third power. I think I miswrote that. Yep. All right. So from here we can substitute in and change out tan squared theta plus 1 instead with secant squared theta. So we're going to get from alpha to beta, lambda b squared secant squared theta d theta all over 4 pi e to the initial times b. Now we can, I'm just going to simplify this right away, but because it is the square root of secant theta just equals secant theta to the third power. All right, from here, now we're going to have from alpha to beta, of lambda b squared, secant squared theta d theta, all over 4 pi times e initial times b to the third power secant third power theta. And now we can do a little bit of simplification. So we're able to get rid of this b squared up here and able to get rid of that 3 down there. And we're also able to get rid of that secant squared up there and get rid of the 3 down there. So now what we have from alpha to beta, we have lambda d theta over 4 pi e initial b secant theta, in which secant theta is just 1 over cosine. So we will rewrite this once again from alpha to beta to be lambda cosine theta d theta over 4 pi e initial times b. Now I want to take a look to see what we can actually take out. So charge per density per unit length and free permittivity. I know we can for sure take the 4 pi out. I'm pretty sure we can also take those two out. I think that's a constant, and I think this is a constant. So we'll just take them outside real quick. So we're going to have lambda over 4 pi e initial times the integral from alpha to beta of cosine theta. And I believe, wait, can we also take out beta? Or no, take out the b? And we are able to take, actually no, b is a point. I think we can take the b out. So that would just be cosine theta d theta. Now we're going to need to draw our right triangle. And I'll check these answers afterwards because I could be wrong and we might need to keep some of those terms in, but by the looks of it, it looks like we should be able to take them out if they're all constants. So we're going to have theta, our right triangle right there, and we said that x equals b tangent theta. So x over b equals tangent of theta, and tangent equals opposite over adjacent. So that means that this is going to be x, and this is going to be b. And as we can saw earlier, it's probably going to equal right here, which it does. So this will be equal from a squared plus b squared equals c squared. We are going to have x squared plus b squared. So for cosine, so cosine of theta is going to equal opposite, adjacent over hypotenuse. So we're going to have beta over the square root.
I believe you need to.
Oh, I need to integrate. I'm getting ahead of myself. So this is going to be equal to lambda over 4 pi e initial b. And then this is going to be cosine, the integral of cosine is sine theta from alpha to beta. Now instead we need sine theta. So sine theta is going to be opposite over hypotenuse, which is going to be equal to x over x squared plus b squared, times which is the square root of that. So we're going to get lambda times x, all that over. Actually, no, we don't need that yet, my bad. We'd have to distribute that, which would be too much of a pain to deal with right now. So we're going to have to evaluate this. So this will just be, actually not, we'll have to evaluate x over square root of x squared plus b squared. And then let's figure out what we're evaluating it from again. So it's going to be from opposite to a to L minus a. All right. So now we're going to get it equal to lambda over 4 pi e initial times b, we're going to set x equal to L minus A. So L minus A over the square root of L minus A squared plus B squared minus, we're going to do opposite A and for x. Okay, and I don't think we can do anything else in terms of simplification, except we can cancel out that minus and turn it into a positive right there, and we can get the that negative will become a positive. So we're going to have lambda over 4 pi e initial b times L minus A over the square root. Actually, this is able to be expanded. So L squared minus A squared actually, wait, no, that should be minus 2LA minus A squared plus B squared. I don't know if we needed to expand it. Probably not.
I don't think so.
Yeah,
On Razor on that. Simplest explanation is usually the best.
Yeah.
The correct one, anyways.
And then there's all that plus alpha over square root of, or no, not alpha, just A over the square root of A squared plus B squared. Okay, now let's take a look at, just to make sure that this is correct, as this is probably by far one of the harder problems that we're going to have to do. Alright, so lambda over 4a times the initial b, and then on the inside we have L minus A over the square root of L minus A squared plus B, and I forgot to put the square down here, plus A over A squared plus B squared. That is the solution for that problem. And
it's not that hard if you take out all the constants, because when you do that, it actually just becomes a regular trig integration problem.
Yeah, so it just looks a lot more dangerous than it should.
Yeah, because it's got all those weird things.
Yeah. So, I guess I should ask, is there any questions that anyone would want to go over, or should we call it at this for tonight? We're currently at an hour and 30 in the second session, and I plan on uploading these after, so if anyone has anything else that we want to hit for section 6.2, yeah, now might be the time. Okay, I'm going to take that as no. I'm going to thank everyone here for enjoying the suffering with me, and hopefully I'll have the recordings up in a little bit in case you want to view one of the other problems, or how terribly I did at integrate this section earlier.
Worry not, your suffering was not in vain.
Yes. I learned a lot through my suffering, and hopefully everyone else can. Okay, I'm going to end the recording now.